Hello, my name is Nilav, and my project is Case Study in Recognition of Emotion from Images. Facial emotion recognition is a fundamental problem in affective computing and human computer interaction. This study presents a convolutional neural network, a CNN based approach for classifying human emotions from facial images. In this work, I present a CNN based facial emotion recognition model trained and evaluated on FER2013 dataset. It's a widely used benchmark for emotion classification in unconstrained settings. I evaluated this particular dataset with other datasets like CK Plus and AffectNet datasets, and then finally settled to FER2013 dataset. The design model processes low resolution grayscale facial images and predicts one of the seven discrete emotion categories: angry, disgust, fear, happy, sad, surprise, and neutral. The model and the supporting system incorporates data normalization, data augmentation, class imbalance handling, and a deep convolutional architecture with batch normalization and dropout regularization. The model shows 61% validation accuracy for the developed model after training for 60 epochs with around 35,000 approximate images. Experimental results on the test data set demonstrate that the model achieves competitive accuracy on the FER 2013 benchmark while maintaining its architectural simplicity and computational efficiency. The software and hardware settings which I needed are as below: Python, TensorFlow 2.17, Keras 3.12, Jupyter Notebook, NumPy 1.26, Panda 2.33. I used Apple Laptop M2 2022 Apple MacBook Air with a GPU of 10 gigs. Are about the dataset. CNN-based emotion recognition model designed, trained, and evaluated on FER 2013 dataset. It's a widely used benchmark, as I said before, for emotion classification in unconstrained settings. The FER 2013 dataset consists of around 35,000 grayscale facial images, each with a resolution of 48 into 48 pixels. The images are labeled into seven emotion categories: angry, disgust, fear, happy, sad, surprise, and neutral. The dataset is distributed as a CSV file containing three fields: emotional labels, pixel values represented as space separated integers, and usage indicators specifying training, validation, and test splits. Below is a screenshot from my Jupyter notebook from the project, where I have used FER 2013 CSV file, and you can see its data count. Data processing. Each image in the dataset undergoes a series of pre-processing steps prior to the training. The pixel values stored as strings are passed into numerical arrays and reshaped into a three-dimensional tensor of 48 into 48 into 1 to represent grayscale images. Pixel intensities are normalized to improve numerical stability and convergence during optimization. You can see the screenshot from my notebook below. The image height is 48, image width is 48, and the number of channels is 1. In the pre-processing, we split each string into a list of floats. Then we go through normalization and reshape to n 48, 48, and 1. You can also see that there are three sets of data: training data, public test, and private test. Public test is for the validation test, and private test is basically the held out test, which we will use in the testing later. Data augmentation. To enhance model generalization and mitigate overfitting, on-the-fly data augmentation is applied during training. Augmentation techniques include random horizontal flipping, small rotations, and zoom transformations, enabling the model to learn more robust representations of the facial expressions, as you can see in the screenshot below. These operations simulate realistic variations in facial orientation and scale, enabling the model to learn more robust representations of the facial expressions. Getting into the architecture, it's a CNN model. It's a deep convolutional neural network architecture composed of multiple convolutional blocks, as on your right hand side. There's block 1, block 2, block 3, and block 4, including the flattened and the dense layers. Each convolutional block consists of two convolutional layers with ReLU activation, followed by batch normalization to stabilize the learning, max pooling for spatial downsampling, and dropout for regularization. The number of convolutional filters increase progressively across the blocks. It moves from 32 to 64 to 128 and then 256, allowing the network to learn hierarchical representations ranging from low-level edge features moving on to high-level emotion-specific patterns. The extracted feature maps are flattened and pass through a dense layer with ReLU activation. A dropout layer with a high dropout rate is applied to reduce overfitting. And finally, a final output layer employs a softmax activation to produce a probability distribution over 7 emotion classes. You can see the screenshot from my Jupyter notebook on the right hand side. Strategy. The model is trained using the Adam optimizer with a fixed learning rate, 1e minus 3. The sparse categorical cross entropy loss function is employed as the emotion levels are encoded as integers. To address class imbalance in FER 2013 dataset, class weighting is applied during training, ensuring that underrepresented emotion categories contribute proportionally to the loss function. Training is controlled using early stopping based on validation loss to prevent overfitting. Model checkpointing is employed to retain the best performing model according to the validation accuracy. This is the training strategy screenshot from my Jupyter notebook. As you can see, the class weights have been applied, and then the model is compiled by using the Keras optimizers Adam optimizers, and then sparse categorical cross entropy as loss with metrics as accuracy. We also have the checkpoint path for best FER 2013 CNN.keras to preserve the best model. Then we run 60 epochs for training. Going moving on to going or moving on to model performance, 60 epochs are run for training. 61% validation accuracy is achieved, along with 59% training accuracy. The test is unseen during training and the model selection to ensure unbiased performance estimation. The trained model accepts either single images or batch of images and outputs predicted emotion labels along with associated confidence scores derived from softmax probabilities. Results indicate that the proposed CNN effectively learns discriminative facial features despite the low resolution and noise present in the FER 2013 dataset. Certain emotion pairs, such as fear and surprise, or sad and neutral, remain challenging due to visual similarity. We will see that in our notebook demo. The overall performance demonstrates suitability of deep convolutional architecture though. With FER 2013, the overall performance is demonstrated overall performance demonstrates the suitability of deep convolutional architecture. As you can see, the screenshot for the validation performance and test performance is given below. To model performance demo, as you can see, When we run a particular image through the model, we see its true label is basically pointing towards the emotion being angry, and the model is predicting correctly that the emotion is angry as well. With 61% accuracy, the confidence level is not so high. Confidence is 0.35. When we plot it, though it is though the true label is equal to the predicted level, we don't see a very high confidence level for the complex emotions. We do see a high predictive level for easy emotions or kind of redundant emotions like happy. Moving on now, you know, getting 10 images from the test set, we compared them against the model, and we see for for different images we have different confidence level, and many of them are predicted correctly while many of them are not predicted correctly. Like regular emotions like happy, uh, you know sad, then angry are mostly correctly predicted, but complex ones like surprise to sad or neutral to sad, which are very similar in nature, uh, they are sometimes missing the mark. So as you can see from the first picture, we can see that the angry to angry prediction is there, but confidence level is 0.35. The second one doesn't meet the mark. The third one with neutral and sad also is zero point 0.4 for confidence. The fourth one with sad and sad, though the confidence level is low, it is predicting correctly. Fear and surprise are so close. Basically the model, uh, the FER data going through the model is not basically removing the confusion, and it is still 0.36 from the confidence level. The angry is met with the correct prediction. The other another picture about sad and neutral, again, so close, and somewhere the confidence level is sitting in the middle of it. For happy, you can see a high level of confidence because a smiling face uh, is typically considered as a general emotion, predictable emotion. Let me use that word, predictable emotion, and hence the model does not have a problem in identifying, the correct emotion here. For angry and angry, the model basically predicting angry to angry with a confidence level of 0.66, which is a good confidence level. As same for happy and happy, which is sitting at 0.53. So I ran through many other images as well, uh, and here is my notebook. Uh, I have basically used TensorFlow and Keras for this particular implementation. As you can see, used FER2013 CSV file, and then I have labeled the emotions: angry, disgust, fear, happy, sad, and surprise, neutral. Each, as we discussed, each image has gone through a series of pre-processing as below. The pixel values stored as strings are passed into numerical arrays and then reshaped into three-dimensional tensor of 4848 into 1. Uh, the FER 2013 CSV file is divided into three types of data set: training, public, and private test. And we are basically using each one for its own purpose. Uh, there are 7 classes because there are 7 types of emotions we have mentioned. To improve training efficiency and scalability, the pre-processed data is then converted into TensorFlow datasets using batching, shuffling, and prefetching operations, as you can see below. Moving on, we do data augmentation by doing random flip, random rotation, and random zoom. We talked about the model architecture. which is having like four convolution blocks with flattened and dense layers. The convolutional blocks having multiple convolution network layers. As we have seen, two convolution network layers with ReLU activation, followed by batch normalization to stabilize learning, max pooling for spatial downsampling, and dropout for regularization. And then moving on, using the class weights uh, to ensure that underrepresented emotion categories contribute proportionally to the loss function. Then we compile the model with different optimizer loss and metrics, Adam optimizer. We then save, the best model, which is trained by running 60 epochs. Then the run happens. There's an early stopping at the accuracy validation accuracy being at 61,215, 0.61215, that is 61.215%. And we then measure the validation performance. We see the same 6121 with test performance being 0.6261. Uh, then we run our image through the model. First, we take a sample. We see the prediction is correct, angry to angry, though the confidence level with a low validation accuracy, which is the 61% for the model, the confidence level is sitting as 0.35. And then we actually take different samples from the 2013 test set, run it against the model, and as we discussed earlier, we see different one-to-one pairing. Some of them are correct, some of them are not. Regular emotions like happy and angry are identified correctly, some with high confidence levels, some with not. The complex emotions, some which are facially very close, cannot be distinguished from each other, like neutral or sad, or surprise and sad, or fear or surprise, are basically not working out so much with low confidence scores. So this is what my model was all about. This is my case study around emotion recognition from images using FER 2013 dataset. Thank you for watching my video, and thank you for basically taking a look at my model.